Well, in linear algebra, eigenvalues and eigenvectors are fundamental concepts found in engineering, applicable also in scientific and mathematical areas. Given a square matrix, say A, an eigenvector, usually denoted as V, is basically a non-zero vector that when multiplied with the matrix, usually of course a square matrix, results in a scalar multiple of itself, and mathematically it can be expressed as this. So where the matrix A is a square matrix, and of course the vector is also a non-zero n-dimensional. N in this case is also the number of rows, which of course is equal to the number of columns for a square matrix. So the dimension of the non-zero vector will correspond to the number of rows and the number of columns. The number of rows basically, or the number of columns, of course, which are the same. So lambda is a scalar, which is the eigenvalue. Now, let me just briefly explain some properties so you can begin to have an apprehension of the applications of eigenvalues and eigenvectors. Now, you see the sum of eigenvalues, we are yet to determine any one, of course. I will be going into examples in the next slide. However, so the sum of eigenvalues of a matrix is equal to the trace of A, which is the sum of the diagonal element of A. So when you have a matrix, you know the diagonal element. Here when you have a matrix in this form, A, B, C, this is B, D, E, F, G, H, I. So the diagonal element in this case is this. So what we are saying is that the sum of the eigenvalues of a matrix is equal to the sum of the diagonal elements. All right. We'll work more on that later. So you can have a better understanding of what we are trying to say. All right. So furthermore, product of eigenvalues gives the determinant of a matrix. So by the time we begin to solve, you can just after solving for the eigenvalues of a matrix, you can try it out. You can try this out to know if the product of the eigenvalues gives the determinant of the matrix. There is also a property called orthogonality. So for symmetric matrices, the eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. And finally, if two matrices A and B are similar, then they have the same eigenvalues. Well, it is important to know the applications of various mathematical concepts so as to better appreciate them when you apply them. For eigenvalues and eigenvectors, the application spans across various engineering fields. For example, in vibration analysis, eigenvalues, which is of course mostly related to mathematical engineering field. So eigenvalues are used to determine the natural frequency of a system, while the eigenvector represents the corresponding mode's shape. Also in quantum mechanics, say quantum physics, eigenvalues corresponds to observable quantities like energy levels, and the eigenvector represent the corresponding quantum states. Of course, it is also useful in principal component analysis. It is also very applicable in system stability analysis. And here, for example, some mathematical systems such as mass spring damper system, the natural frequency, which is relative to the eigenvalues, determine how the system will oscillate when disturbed. So, and you see, engineers use these eigenvalues to design systems that avoid resonance, where oscillation could become dangerously large. In image processing, it is very also helpful in extracting important features from an image. Take, for example, facial recognition. So we can then move on to solving eigenvalues and eigenvectors. So let's consider a 2x2 matrix. We can just start from this elementary one. I want to find the eigenvalues and eigenvectors for matrix A. So in order to find the eigenvalues, we subtract the lambda multiplied by the identity matrix from A, and we just simply find the determinant of what we get. And remember, we set the determinant to 0 to be able to find the eigenvalues, which are the lambda. So for this matrix A, we just try to transform this matrix into this form. Of course, this is A, and we do it this way, minus, we also want to consider this aspect, lambda multiplied by identity matrix I. So now, this is lambda, and this is an identity matrix. So we just simply subtract this, the product of lambda and this identity matrix, from this matrix, and we try to find the determinant. So when we multiply 1 by this identity matrix, what we just get is the scalar the lambda here and lambda here. So then when we subtract this matrix from all this, you see, just simply subtract the corresponding like elements in like positions. So what that means is 4 minus lambda, because both of them occupy the same position, that is the first row and first column. So 4 minus lambda, of course we've got lambda here, and this will be 1 minus 0. so that will be 1. And this 2 will be 2 minus 0, that will be 2, and 3 minus lambda, of course this is lambda, and that is what we've got there. So the next step is to find the determinant of this, and of course we've been setting it to 0. So please note that we've got 0 here. That is just an omission. Okay then, so calculating the determinants, we then say 4 minus lambda multiplied by 3 minus lambda on this side. So we subtract, we say minus 2 times 1, and we also set that to 0. So then when you multiply this out and you subtract it from this, you get this. So this can be solved using various methods. You can decide to factorize, you can decide to use equation, you can decide to factorize. If you want to factorize, you say 10 multiplied by lambda square, that will give you 10 lambda square. So on this side, then what you've got here is minus 7 lambda, minus 7 lambda. So what two values when multiplied will give you these, and when you add them will give you this. So let's look at 2 and 5. 2 lambda and 5 lambda. So if you say minus 2 lambda times minus 5 lambda, it will give you 10 lambda square. Then if you say minus 2 lambda minus 5 lambda, it will give you minus 7 lambda. So you can just basically now come here and say lambda squared minus 2 lambda minus 5 lambda plus 10 equals 0. So of course this is factorization method. Minus 2 lambda and minus 5 lambda of course gives you minus 7 lambda. So you just decided to instead of writing it this way, you've just written it this way. And with that you can then further factorize. What is common between these is lambda, and you bring in, if you say lambda times lambda gives you lambda squared minus 2. All right, between this and this also you have minus 5, then that gives you lambda, so that you can have minus 5 times lambda, it gives you minus 5 lambda, then minus 2. So that minus 5 times minus 2 will give you 10 plus 10, so equal to 0. So then it then means that you have lambda minus 5. It is either lambda minus 5 equals 0 or lambda minus 2 equals 0. So when you do that, either this or this equals 0. So if this equals 0, you have lambda equals 5, and if this equals 0, you have lambda equals 2. So this is the factorization method. Of course, you can also use this formula equation in finding and solving the problem. So yes, so these are then the eigenvalues for this matrix. the first eigenvalue is 5 and the second eigenvalue is 2. Now usually after finding the eigenvalues, the next step will be to find the eigenvectors. So the first eigenvalue is 5. So in order to find the eigenvector, we set the equation in this form. So this is the general form of equation used to determine eigenvectors. So when the eigenvalue is 5, so we just simply set the lambda. We substitute 5 for lambda in this equation. So writing down the whole problem in this form shows that we have matrix here, the matrix A minus the eigenvalue, which we want to use to find the eigenvectors, and the identity matrix. So you see, multiplying 5 with this identity matrix shows that we'll have you get the 5 here and the 5 here. Of course, this remains this guy here remains 0. So then see that 4 minus 5 will give you minus 1. 1 minus 0 will give you 1. 2 minus 0 will give you 2. And 3 minus 5 will give you minus 2. So that's how the whole of this transforms into this. Then this vector is our eigenvector, which we want to find. So then it has to be in this form. So we can, this vector has to be in this form, so we can determine the eigenvectors. So remember the difference between this and this. You can see this is italicized, split it into 2 to correspond with the number of rows, and this is you see bolden. So kindly note that there's a difference between writing this one and presenting it in this way. All right then, so this results in the system of equation. Now if you look at this, of course you can transform this into the linear equation form. However, a close look, critical look at this shows that you see you've got a set of equations where the order is a multiple of the first. So, and in linear equation, there's a name to that. Think infinite solutions. So, but for this type of problem, what we'll do is that we will just pick one of them. Any of them will give you the same solution. So let's just pick this, transform it into the linear form, which will be minus 1 v1 plus v2 equals 0. So then, and this is what we've got, so we can then proceed with this, and that will show that v1 equals v2. So, and if v1 equals v2, it then means that this, now writing it down in this form, is the eigenvectors. For this first one, of course, we have eigenvalue 1 and eigenvalue 2. So we can then say, okay, for this eigenvector 1, this element of the eigenvector, we can assume it to be 1. And because v1 equals v2, of course, if v1 equals 1, v2 will be equals 1. Because any value for v2 will be equals to that of the v1, and any value for v1 will be equals to the value for v2. So basically, assuming 1 for v1 is just the basics, and it is true for all values basically. So we can assume 1 for v1 and 1 for v2. 2 here. So then this becomes the eigenvector for the eigenvalue of 5. So let's move on with the to finding the eigenvectors for the eigenvalue 2. So in the same way, we transform the whole matrix into this form, and this is the matrix A minus this is the scalar value, that is the eigenvalue, minus 2, and the identity matrix. So that means the 2 multiplied by 2, 1 will give us 2 here and 2 here. Of course, this will remain 0, 0. So 4 minus 2 will give us 2, 1 minus 0 will give us 1, 2 minus 0 will give us 2, and 3 minus 2 will give us 1. So we can also write it in this form. And of course, you discover that this also gives us such kind of problem where it is just a multiple of itself. You see, the same, to give you the same class of, the same set of linear equation. So we can just pick one of it too, just similar to this, where we have a multiple of one of it giving us a multiple of the other. So we then just pick one of it, which is 2 multiplied by v1, 1 multiplied by v2, and that's what we've got here, equals 0. So this will show that v1 equals minus 1 all over 2 v2. Now, because this is v1, so we can then say this eigenvector can be represented as minus 1 all over 2, and of course, if say v2 equals 1, then v1 will equal minus 1 all over 2. This shows that whatever the value of v2, v1 will be half of that value, minus half of that value, and that is what we've just basically represented here. So now we want to move on that, having looked at the elementary ones. We want to move up to a matrix of a higher order, 3 by 3 matrix. So we want to find the eigenvalues of and eigenvectors of this matrix A. So the first step here then will be to find the eigenvalues. So and in order to find the eigenvalues, we have to use the characteristic equation for doing that. Now this is the characteristic equation for doing that. That is subtract lambda multiplied by the identity matrix from matrix A and set it to 0. Then look for the determinants of that whole equation. So then, and you know, for an identity matrix, you have the diagonal elements being 1 all through, which shows that when you multiply that with lambda, you'll have lambda all through in the identity matrix. Of course, the off diagonal elements are all 0. And because of that, it'll then mean that we then subtracting that from matrix A will simply show that we are subtracting lambda from the diagonal elements, which will be 3 minus lambda, 2 minus lambda, and 5 minus lambda, as these are the diagonal elements. So basically this transforms to this. Now we can calculate the determinants of this matrix, this O matrix here. Now, and in order to do that, of course, there's a rule to doing that. Now, since This is an upper triangular matrix. The determinant is simply the product of the diagonal elements. Well, you can find the determinant of these, by just setting this first element here in the first row and the first column. Then you look for the minor, the diagonal, the matrix of the minor, and the matrix of the minor, the determinant of the minor, that is the 2 by 2 matrix that will be left here, will simply be multiplication of this value with this value minus 0. You understand? Now, and that is what you've got here. And well, when you minus 1 minus this one, and because this is 0 and this is 0 and this has values, when you multiply this with this, it gives you 0. When you multiply this with this, it gives you 0. And 0 minus 0 gives you 0. So 0 times 1 gives you 0. And that is why you have nothing after that. The same thing applies here. 4, when you say plus 4, and you want to find the determinant of this minor, it will also give you 0. And that is why this basic rule holds. For the upper triangular matrix, the determinant is always just when you see a upper triangular matrix, just know that the determinant is the product of the diagonal elements, and this gives us the determinant of the matrix. So then we set the determinant equal to 0 to solve the eigenvalues. That is what the characteristic equation says. So when we do that, it then means that when we set all this to 0, then it then means that either this equals 0, this equals 0, this or this equals 0 for the equation to be true. Therefore, if this equals 0, then lambda 1 will equal 3. And if this equals 0, lambda 2, as the second eigenvalue, will be equal 2. And if this equals 0, the lambda 3, which is the third eigenvalue, will equal 5. So then the next step will be that we should now proceed using these eigenvalues to find the eigenvector. So for each of the eigenvalues, we will then use these eigenvalues to solve for the eigenvectors. But the characteristic equation used in solving for the eigenvectors is this and not this time around. So of course, where V is the eigenvector corresponding to the eigenvalue to be solved. All right. So we start by finding the eigenvectors for each of the eigenvalues. So starting with the eigenvalue lambda 1 equals 3. Then we substitute 3 for lambda in this equation. So, and you remember that the matrix A equals this. So when we substitute 3 for lambda here, that will be 3 multiplied by the identity matrix, and the identity matrix is such that you have the diagonal element being 1. When you multiply 3 with the diagonal elements being 1, what you get is something like this for the identity. Oops, it's a mistake. Okay, so okay, so then when you subtract this from this, it'll be 3 minus 3, that will give you 0, and of course every other thing will remain because 1 minus 0, 4 minus 0 gives you 1 and 4. So basically what's will be changing is the diagonal element. So 3 minus 3 will give you 3, 2 minus 3 will give you minus 1, and 6 minus 5 minus 3 will give you 2. So that is that about that. Let's get this guy. So all right then. So now this is what it transforms to. So we can then solve the system of equation using the characteristic equation for solving eigenvectors. So we then have it in this form. Now the system of equations that would be produced from here is unlike the elementary one we did the other time. So we can then proceed to creating the system of linear equation here and maybe transform them into the row echelon form. So for this third row, we have it that this is 0, this is 0, and of course the coefficients of v1 and v2 is 0. So then we can then say that 2 multiplied by v3 equals 0. So this shows vividly that v3 equals 0. So now if we now have a value for v3, then we can then solve for v2 in using the second row. So then from the second row we have that this multiplied by this multiplied by this, and this multiplied by this. Of course, this multiplied by this gives you 0. Then minus 1 times v2 gives us minus v2 plus 6v3 equals 0. When v3 equals 0, as it has been established here, then substituting 0 for v3 here shows that minus 2 will also equal 0. So now we've got the value for minus 2, and we've got the value for v2, and we've got the value for v3. So it then means that v1 is free. We call v1 free because from here basically there is no value for v1. All right then. So now the eigenvector corresponding to eigenvalue that equals 3 will be such that v3 equals 0. Of course, this is v1, v2, v3. So v3 equals 0, v2 equals 0. But v1 is free in this case. So, and when you have a vector value being free, it means it can be any value. So you can just assume a 1 for it in this case, because 1 is also a value. In fact, the simplest form of the values you can get. So this is how the eigenvectors for the eigenvalue 3 is found. Okay, so let's move on from here. Eigenvector for the eigenvectors for the second eigenvalue. So again, in this form, you subtract 2 from this, 2 from this, and 2 from this, and when you do that, you get 1, 0, and 3. So this becomes the form of what you proceed with, and that is what we've got here. So the eigenvectors, transforming it, or just trying to write out the whole thing in form of the characteristic equation for solving for eigenvector makes it then looks like this. So we then just proceed from here to, so then the equation becomes this. So again, from the third row, we found that v3 will be equals to 0, and which shows that v3 will be equals 0. So from the second row too, we see that v3 also equals 3, of course. So, but from the first row, we see that we've got V1 plus V2 plus 4V3 equals 0. And this shows that V1 will definitely equals to the negative value of V2. And of course, you will see that from the second row here, it is established that though V3 equals 0, but there's no new information with respect to V1 and V2, and that is why proceeding to the first row here provide that useful information. So then it is like the rule, the basic trick, because V1 equals V minus V2, it then means that whatever the value of V1, it will definitely correspond to the negative value of whatever the value of V2, V1 will be the negative of that value. If it is 1,000, it will be the negative of 1,000. So, and the least and the simplest form to represent that is to consider V2 to be just 1. And of course, like mentioned earlier, 1 is also a value, like a million, like a trillion, and so on and so forth. So basically, representing it as 1 will show that V1 will equal, if V2 is 1, then definitely V1 will be the negative of that value. And of course, we had established that V3 equals 0. So we can then proceed to the third eigenvalue to determine the eigenvectors for that. So, a similar way, we simply subtract this eigenvalue from the matrix using basically the diagonal elements. So when we subtract all the 5 from all the diagonal elements, this is what results. So we then begin to solve the system of linear equation, and in doing that, we discover that beginning from the second row, we found that we've got minus V2 plus 6V3 equals 0. It then means that V2 will be equals to 2 multiplied by V3. And from the first row, the information here is that, playing around with that, minus 2 multiplied by V1, 1 multiplied by V2, and 4 multiplied by V3 equals 0. So we then have minus 2V1 plus 2V3 plus 4V3 equals 0. So while playing around with that shows that we've got minus 2V1. When you substitute 2V3 for V2, 2V3, and when you add this together, you have 6V3, and that is what you've got here. So it then means that V1 will be equal to 3V3. Therefore, the eigenvector corresponding to this eigenvalue is, this is V1, V2, and V3. So V1 will be equal to 3 multiplied by V3, and V2 will be equal to 2 multiplied by V3. So we just basically assume, in that case, we just basically assume a 1 for V3, so that 3 multiplied by that 1 will give us 2, and of course V2 equals 2 V3, and 3 multiplied by that value will give us 3. So that is how to solve that.